If you remember, a few blocks back, we began to look at the type classes that were built into Haskell, and we looked mainly at the numeric type classes and some of the simpler ones like EQ and ORD. What I want to do in this section is to look at what we didn't look at then, namely the type classes at the bottom of the diagram. These are the ones that represent mappable and foldable, and building on top of mappable we get applicative and we get the idea of monads. And I'll talk about each of those type classes except traversable in segments to come in this block. I want to introduce a piece of terminology now before I talk about mappable types. We talk about a functor as a function taking types to types. So, for example, maybe is a functor. It takes the type int to the type maybe int, which is a type of maybe integers. Similarly, we can build trees of a particular type. That's applying the tree functor to a particular type like int or bool. And similarly, you can think of list formation as a functor. It takes a type like bool to the type of listabool. So functors are these things that take types to types. And often, many of these type functions, these functors are mappable, so that if we've produced a something like a list of bool, we can turn that list of bool into list of int by taking a function that turns bools to int and applying it to each element in the list. So let's reflect that in a type class definition. And what we say here is the class functor of G. So for G to be in this type class, G is a functor, it's a function from types to types. What do we have to do? Well, we have to have a thing called fmap, which when given a function from A to B and something of type G of A gives us back something of type G of B. Where G is the list formation, this is just the familiar map function that you see on the left. But what we do in general is we traverse the data structure, typically recursively, and we apply f to anything of type A that we find. And that's how we declare an instance of that functor type class. So we know the definition for lists, but what are these other types? Well, one example is the maybe type. You remember the maybe type? There are two constructors. One is the nothing and the other is just an A. So it essentially says you either get something of type A or you get nothing. And what does fmap do over that type? Well, if we apply fmap of f to nothing, we get nothing. Whereas if we apply fmap of f to just of x, f can be applied to x and return just of f of x, which is of type maybe of B. We start off with something of type maybe of A, so x is of type A. We finish up with just f of A, which are f of x, which is of type B. So we get, it's taken something of type maybe of A to type maybe of B. Okay. A bit more complicated, we can do a similar thing for a binary tree. We can map across all the objects of type A inside a tree. And remember, here's the type of the tree here on the left. It's either a leaf or it's a node with a left subtree, a value of type A, and a right subtree. What do we do to apply f to every thing of type A in the tree? Well, if we apply fmap f to a leaf, we get a leaf. If we apply fmap of f to a node, we recursively apply fmap of f to the left subtree t1 and the right subtree t2, but we apply f to that value x of type A that's sitting there at the node, and that gives us a value of type B. So that runs through, and you can see we have mapped here. The tree is a complicated structure, but at each internal node there's a value of type A, and what we've done is apply f to transform that to something of type B. And of course, we shouldn't forget lists themselves. We write the list type constructor by writing open square paren, close square paren, and here I'm defining an instance. For that, I'm saying fmap of f on the empty list is the empty list, and fmap of f on x colon x's is f of x colon fmap f x's. In other words, fmap is map over lists. So there are many more examples, but these are the most important ones, I think. So things like trees, you can map every element of type A to something of type B. In a maybe type, you can transform the one element, and so on. So that's one of these simplest structural type classes. It allows us to uniformly transform things of type A into things of type B across an arbitrary or across very different data structures.